Okay, hi everybody. We're on to our third installment of the different types of weak acid calculations that you might see. Kind of unusual twists and trickiness that teachers can give you, or scenarios that you'll see in a lab or something like that. Today's going to be an unusual one. It's not commonly seen, but it's a good one to remind you of what weak acid solutions are doing. It also is a good reminder of what water is always doing on its own, regardless of whether it has anything in it or not. So it's about finding the pH of a really dilute weak acid solution. And if you think about that, really dilute means not very concentrated. Weak acid, they don't produce very much hydronium because they don't get rid of their H very well. So what happens if you've got this combination of not super concentrated acid and not a very good ability to get rid of a hydrogen to make hydronium? They'll still make hydronium, but perhaps it's not very much. And so you can sometimes get some pretty unusual situations. Okay, so I'm going to do a question about that one right here. The next class is going to be about, if you recall in the original class in episode 6 on weak acids, when you're doing the math and you're making an assumption, and you're dropping an X, kind of doing some fancy magical math, what happens when that assumption doesn't work? So that'll be next class. That's kind of a critical one, because if you've been following along and trying to do the math that I'm doing with weak acids, we always make that assumption. Okay, so what happens when it doesn't work? Okay, but today, what about the dilute, really weak acid? So I've got a question up here to demonstrate this point. This phenomenon is not going to happen all the time. It needs to be a really dilute, really weak acid for you to get into this scenario, but it's something to always kind of keep in the back of your mind. Okay, so the question is really, it's fairly straightforward. It just looks like a regular, everyday, weak acid type of question. What is the pH of 0.0020 molar H2O2, which is hydrogen peroxide? So if you take a really dilute, I guess it's not really dilute, but it's pretty dilute, 0.0020 molar hydrogen peroxide solution, what is its pH? Okay, so hydrogen peroxide is an acid, and so if you've got your Ka table, you'll scour it for hydrogen peroxide, and I'm looking, where is that thing? It's way down here. Okay, so hydrogen peroxide is like literally in this one, it's like third from the bottom in the white section. Okay, so H2O2 is way down there. As an acid, it sucks. So not only does it suck as an acid and doesn't make very much hydronium, even if it was concentrated, it doesn't even make very much of it. Now we've got a dilute solution of it, so it's barely going to make any. So we should be anticipating that. But if we've got this question, and even if that all of that didn't cross your mind, you'd go, well, pH of a weak acid, cool, let's just do the question. So H2O2, weak acid, it's on the table. H2O2, molecular solution, put it into water, produces hydronium, and I guess it's kind of unusual. What's the formula of H2O2's conjugate base? Well, you remove an H because it's gone onto the water, so you're down to one H, still has the two O's, and now it's got a negative charge. That's unusual. Little ion, and there you go, that's what you've got. IRE table. IRE. Once you start going faster, you start to get a little bit messier with your IRE tables. Water's liquid, so we cross it out. Liquids don't change concentration, so we cross them out. They're not part of K expressions or equilibrium constants. I plug in what I do know, which is the initial concentration of the acid. Very dilute. I also know zeros across here. I don't know anything about equilibrium. I do know that it goes, so the reaction goes in the forward direction. This will be down, this will be up, and this will be up. I do not know how much, so we're using X. And so there's my IRE table filled in. Granted, it's got variables in it, but no big deal. That's what we're trying to do. We're trying to solve for the equilibrium concentrations. Next step was always K expression. So the formula that you're going to use to do your math. So I'm going to make sure I leave a little bit of room over here. Hydronium times that weirdo thing over H2O2. There's my K expression. Plug in the values. So I need to get the Ka off the table. I need my glasses because I cannot see it. Hydrogen peroxide, 2.4 times 10 to the negative 12. 2.4 times 10 to the negative 12 equals x squared, x times x, over 0020 minus x. Okay? At this point, right, you have two pathways at this point. You've got an equation that you could multiply it all out, and you could put the x squared, the x, and the constant term on one side and equal 0, and you could use the quadratic formula. You can do that, right? And if you're in the habit of doing that, or your teacher wants you to do that, or whatever, then it works. Go ahead, do it. But you can do the assumption. So at this point, you can make an assumption. And the assumption always has to do with that bottom of the fraction where you're subtracting the x from a value. And the assumption is always, it's always based in this theory. So I'm going to remind you that it's based in the theory that whatever x is going to be, it's going to be teeny relative to the number you're subtracting it from. Now by teeny, I mean insignificant. So if you follow sig fig rules, it will not change it even if you do the subtraction. It's going to round back to the same thing. Okay, so that's the assumption that we're going to make, and it works 99% of the time. Next class, we'll go over when it doesn't work. But I write it down, so I'm going to assume that x is going to be significantly smaller than 0.0020. Now that goes to 4 decimal places, so that's, I don't know if my assumption's even going to work in this case, but it's a really weak acid. So chances are it's still going to make a very small amount compared to an already small number. So given that, I can now drop the minus x because it doesn't actually matter. Mathematically, it doesn't matter, and that's why we're making the assumption. So now I do the math. So now I go 2.4 times 10 to the negative 12 times 0.002 equals, okay, I'll take the steps. I'm not sure you actually, the assumption is you guys know how to do algebra, so you could probably just at this point write x equals. I'm going to take the steps. So 4.8, 10 to the negative 15. 4.8 times 10 to the negative 15 equals x squared. So x equals the square root of that. So x equals root equals 6.9, 2 sig figs, correct? Yes, 2 sig figs, 6.9 times 10 to the negative 8. Okay, so there's the mathematical answer to whatever x is. Now x stands for the hydronium and this HO2 -1 thing. So there's your hydronium. So now I guess you write down hydronium at equilibrium equals 6.9 times 10 to the negative 8 molar. Now, I'm going to pause just for a sec. If you negative log that, go ahead and do it. Like, pull out a calculator, plug in 6.9 times 10 to the negative 8, negative log it. I'll take a break. I'll do it. You do it. So, my computer will fade to black and fix that. So 6.9 times 10 to the negative 8, I negative log that guy, and I get 7.16. Is that my answer? Now, I want to stop and I want you to think logically for a minute. This is at 25 degrees. What is neutral at 25 degrees? You know it. You've known it since whenever you first learned about acids, like way, way back. So pH of 7 at 25 degrees is neutral. We just got a pH greater than 7. So, based on all your previous knowledge, is this acidic, basic, or neutral? Well, it's barely above 7, but it is above 7, so it's barely basic. What? This thing's acting as an acid. How does a chemical acting as an acid make a solution basic? Like that? That is an impossibility. You're right. That's not correct. Oh, jeez. How do we get a pH of 7.16? It's above 7. Oh, I must have done something wrong. So you go through and you look at it and maybe I should have done the quadratic. Do the quadratic, you get the same answer. Right? You'll get this. It's the right answer. It's the right mathematical answer. The reason it's above 7 is something that maybe you haven't noticed. Maybe you have. Maybe you haven't. Do not forget that back in the original IRE, we make the assumption that that is 0. Is it 0? It's not technically 0. When you take this hydrogen peroxide and dump it into the water, the water, before you even put hydrogen peroxide in it, is already at equilibrium. It already has hydronium of 1 times 10 to the negative 7. Then you add the hydrogen peroxide and it makes a bunch, or makes whatever it makes, and then it adds to that amount that was already there. So this amount right here is added to what was already there. And so if you just negative log this value, yeah, it's actually below 1 times 10 to the negative 7. So you're going to get a pH that looks wonky, but that's not the pH. That's not the actual hydronium in the water. The hydronium in the water is the hydronium is actually the 6.9 times 10 to the negative 8 plus what was already there. So it's actually 6.9 times 10 to the negative 8 plus the 1 times 10 to the negative 7. You put them together. And so therefore, you end up with 1.69 times 10 to the negative 7. Now that value you can take to more sig figs, so that's why I've included the whole thing. So the actual amount is 1.69. It's not 1 times 10 to the negative 7. It's not 6.9 times 10 to the negative 8. It's the two of them combined together, because technically that is not 0 when you add that extra amount to it. Okay, and that's kind of where the trick comes in. So now if you take this and you say pH equals the negative log of the hydronium, you're actually saying it's the negative log of the total hydronium, right? It's not just what the acid gives you in the IRE table. It's what the acid gives you in the IRE table plus 1 times 10 to the negative 7. Now, normally that 1 times 10 to the negative 7 is a very small amount. It's insignificant, as a matter of fact, compared to what the acid typically makes. But we're not talking about any situation. We're talking about really dilute acid and really, really weak acid. So, like, sucking on 2 levels here. So this is an abnormal situation. So in this case, you do have to think of that total. That 1.0 times 10 to the negative 7 is actually a significant amount. So now I'm taking the negative log of 1.69 times 10 to the negative 7. So that's now what I'm doing. So let's do that. So log of 1.69 is 10 to the negative 7, and you get a pH equal to 6.77. Now, that's not super acidic. We're not talking, you know, that's not even as acidic as your sweat is. So that value that's right there is barely acidic. The hydrogen peroxide barely makes it acidic, but now at least it's on the acidic side of 7, and it makes a little bit more sense. An acid making a pH less than 7. Super dilute, super weak, so you would expect it to not be very low below 7. There you go. So that's kind of an unusual kind of twist on that. Don't forget that water always has 1 times 10 to the negative 7, and you're adding on top of it when you do a weak acid. Typically, it's insignificant, so you can ignore it. In this case, you couldn't. Okay, see you next time.